Lecture 5 is Nuclear Magnetic Resonance Spectroscopy, or NMR. This is also the same technology that they use in MRI, magnetic resonance imaging. This is our second part of our spectroscopy series. We're probably going to do this lecture in two parts because there's a ton of information in it, and there is a logical break point between the first part, which is more simple, and the second part, which is more advanced. So NMR is really the most powerful tool available to us in organic structure determination. Last time we talked about mass spec, and there was some critical pieces of information that mass spec provided. For example, it would give us a molecular weight from which we could determine a molecular formula. It gave us evidence of isotopes, for example, of bromine, of chlorine, nitrogen, sulfur, iodine, things like that. And it also gave us clues to the structure of any alkyl skeleton of our molecule. But NMR provides a lot of that information as well, and it makes it a little more clear and does it in ostensibly a better, cleaner way. What it does is NMR observes the chemical environment of an atom. And from that, we can, like I said, provide evidence for the structure of alkyl groups, as well as clues to functional groups. Unlike mass spec, NMR is non-destructive, meaning that our sample can be recovered after we've taken the spectrum of it. We can also use very little material. We need less than 1 milligram typically. And although it cannot separate impurities before analysis the way that GCMS can, impurities can obscure the results, but we can also see them in the spectrum and they can be identified. So even if there are impurities in our sample, the identity of them can be determined, and therefore we can use that information to determine how we're going to be purifying our material, or perhaps how we might change our protocol to eliminate those impurities in the first place. So NMR, we can use it to study a wide variety of nuclei, including hydrogen, carbon, nitrogen, fluorine, and phosphorus. What you'll notice is that these are odd number nuclei. This is hydrogen 1, carbon 13, nitrogen 15, fluorine 19, and phosphorus 31. So these are all odd number nuclei with an odd atomic mass. And some of these are common isotopes. Remember, we saw that carbon 13 occurs in 1% of all carbon. Nitrogen 15, fluorine 19, and phosphorus 31 are also fairly common isotopes of nitrogen, fluorine, and phosphorus. Organic chemists, for the most part, find proton NMR, H NMR, and carbon 13 NMR to be the most useful because hydrogen and carbon are major components of organic compounds. For example, if we are trying to study a molecule that doesn't have any phosphorus on it, then studying or looking for phosphorus 31 is not going to be very useful. It's not going to tell us any information if there's no phosphorus on our molecule. But if we can look at hydrogen or look at carbon, it's going to give us a ton of information about our organic structures because hydrogen and carbon are all over the place in our organic structures. Historically, NMR was first used to study protons, that is to say, the nuclei of hydrogen atoms. And so proton magnetic resonance, what we would say HNMR spectrometers, are the most common, such that if you ever hear somebody says nuclear magnetic resonance, you can assume that they mean proton magnetic resonance, unless a different nucleus type is specified. I want to mention, although the other methods of spectroscopy that we've talked about, mass spec for now, and later on we're going to talk about infrared spectroscopy, NMR is not only the most powerful, but it's mostly put the other methods mostly out of business. There's not a whole lot of extra information that mass spec can provide or that IR infrared can provide that NMR can't already give us at least a clue to. So the general principle of NMR is that a sample is placed in a magnetic field, and that enables the nuclei in our molecule to absorb radio frequencies, typically ranging between 60 and 1,000 megahertz. There's something in a nucleus called the spin quantum number. The variable we use for that is capital I. The spin quantum number of a nucleus is an important property in NMR in that you need to have an odd spin quantum number for the nucleus to interact with the magnetic field. Generally speaking, in quantum terms, each proton and each nucleus has a spin quantum number of a half. And protons will pair and will cancel each other's spin quantum numbers out. And neutrons will pair and cancel each other's spin quantum numbers out. So in hydrogen 1, whose nucleus is just a proton, the spin quantum number is just a half from that one proton. But helium, which is helium-4, would have 2 protons and 2 neutrons. So those 2 protons would cancel, the 2 neutrons would cancel, and our spin quantum number would be 0. We could do the same thing for carbon-12, 6 protons and 6 neutrons. All of those, each 3 pairs of protons and 3 pairs of neutrons, would all cancel each other out. In oxygen-16, we have 4 pairs of protons and 4 pairs of neutrons. And in oxygen-18, we've got 8 pairs of protons and 10 pairs of neutrons. So all of those pairs will cancel each other out, which means that those nuclei are not active in NMR. They do not interact with the magnetic field. Protons will, so we can study protons in NMR. Also, deuterium, which is hydrogen 2. It's still hydrogen, so it's got 1 proton, but it's also got 1 neutron. It's got a spin quantum number of 1, a half from the proton and a half from the neutron. Remember, protons cancel and neutrons cancel, but protons will not cancel with neutrons. So they have a spin quantum number of 1 in deuterium. Carbon-13 has 6 protons. All of those will cancel, but 7 neutrons. 6 of those will cancel, leaving us with 1 unpaired neutron. So that will have a spin quantum number of a half. Nitrogen-15 has 7 protons and 8 neutrons. So all 8 neutrons will pair in 4 pairs. We'll have 3 pairs of protons plus 1 unpaired proton, the 7th. So that will have a spin quantum number of a half. So that means that deuterium, carbon-13, and nitrogen-15 are active in NMR. They will interact with the magnetic field, and that will allow us to study them. The reason that spin quantum number is important is because it determines the number of states, energetic states, that a nucleus can occupy in a magnetic field. Generally speaking, the number of states that a nucleus can occupy in a magnetic field is 2 times the spin quantum number plus 1. And that will basically give us negative I to positive I in integer steps. For example, if our spin quantum number is 0, 2 times 0 plus 1 means that there is 1 state. And if there's only 1 state, that means that there's no spectrum, because a spectrum involves transitions between different states. When we talk about emission spectrum, where atoms emit light, they emit light because the electrons fall down from higher states to lower states, and in doing so they release energy, and that energy comes out in the form of light. So you need more than 1 state to generate a spectrum. If your spin quantum number is a half, then you have 2 times a half plus 1, means that your number of states is 2. So we have 2 states, and so we can have a spectrum. We can observe the transition between those 2 states. For a spin quantum number of 1, your number of states is 2 times 1 plus 1, which means we have 3 states. So now we can observe the spectrum as the nuclei transition between these different states. The energies of these states depends on the nucleus type, not the spin quantum number. That's not super important here, but all that means is that there are different energy states for carbon-13 than there are for nitrogen-15 or than there are for deuterium or for hydrogen. So like we said, a nucleus with an odd atomic number or an odd mass number will have a nuclear spin from the spin quantum number, and that nuclear spin will allow the nucleus to interact with a magnetic field, generate different states, and we can observe the transition between those states with the NMR spectrometer. The proton is the simplest nucleus with its odd atomic mass unit of 1. It has a spin, and it has 2 states. And we're going to imagine these 2 states the same way that we might imagine a dipole interacting with a magnetic field. Here's how that works. We can imagine a spinning proton, which has a charge, as a rotating sphere of positive charge. So think about like a top that's spinning on your desk, a top that's spinning. You can think about that as being a nucleus, and that has a spin associated with it. And so, like a loop of current, you might remember this from physics if you've taken physics at some point. If you have a loop of current, that will generate a magnetic field. If the current is moving in the counterclockwise rotation, the magnetic field will go from the bottom to the top through that loop and will wrap around like it shows here. This is called the right-hand rule. If you imagine your fingers wrapping around in a counterclockwise circle like they do with your right hand, if you hold out your right hand and curl your fingers around, they'll be going in a counterclockwise direction. If you do that, your thumb is pointing up, so that's the direction the magnetic field we're going. That's called the right-hand rule. So the same way that a spinning loop of current generates a magnetic field, so will a spinning proton with a positive charge, or a spinning nucleus with a positive charge, generate a magnetic field. And that magnetic field kind of looks like a bar magnet, the same kind of magnetic field that the Earth generates, for example. And that means that if we have spinning proton or a loop of current that generates a magnetic field, it will interact with an external magnetic field. And we can use that to study the type of nucleus that we have and its environment as well. So here's how that works. In the presence of an external magnetic field, which we call B0, that just is the term or the symbol for an externally applied magnetic field, the nuclei that have their own internal spin and their own internal magnetic field will align with that external magnetic field in one of two ways. They will align either parallel with the magnetic field or anti-parallel with the magnetic field. So imagine that we've got a bunch of nuclei, and if they are not in the presence of an external magnetic field, each one will be kind of tumbling randomly in our sample. And you can see here these individual little arrows are showing how the individual nuclei magnetic fields are aligned. But when we put them in an external magnetic field, they're either going to align with the magnetic field so that their individual dipoles are aligned with the magnetic field, both say up and up, or they will align anti-parallel to it, so down or up. Those are our two states for our nuclei with a spin quantum number of 0.5. It turns out that when the nuclei align with the external magnetic field, that's a lower energy state, and we call that the alpha spin state. And when they align anti-parallel to the magnetic field, we call that the beta spin state. That's a higher energy state. The difference in energy between these two states is determined by the strength of the external magnetic field. And if you think about that, that should make sense. If we have a very, very, very strong magnetic field, then the alpha spin state is going to be very happy because it gets to align with a very strong magnetic field. Conversely, the beta spin state will be very unhappy because it is aligned against a very strong magnetic field. So the stronger the magnet that we can apply, the bigger the difference in energy between the two spin states, which means that we'll basically have louder transitions, more visible transitions as our nuclei transition between the alpha state and the beta state. So all we have to do then is allow the nuclei to absorb some form of energy so that it can transition between the alpha state and the beta state. When the proton absorbs some form of energy, usually it's going to be an electromagnetic pulse of some sort, which we will measure in hertz. It can absorb energy and transition from the alpha state to the beta state as long as the energy that it absorbs is equal to the delta E between the two states. Like I said, the larger the transition, the easier it is to detect, which means that we want a nice strong magnet so we can apply a strong external magnetic field to generate a big difference between our two states. then what we can do is bombard our sample with electromagnetic pulses of different energies, and the appropriate energies will get absorbed so that these states can flip. We can transition from the alpha state to the beta state. Then we can look at what energies were absorbed and infer from that what the magnetic environment is around our nuclei. So when a nucleus is subjected to the correct combination of magnetic field to generate the two states with a delta E and electromagnetic radiation that matches the delta E in order to flip the spin, the nucleus is said to be in resonance, and the absorption of energy can be detected by the spectrometer. This is where the term comes from, nuclear magnetic resonance. So we're going to do two things. We're going to take our sample, we're going to subject it to a magnetic field that will generate different nuclear states, and then we're going to bombard our sample with radio frequencies, and we're going to look at what radio frequencies are absorbed by these nuclei, and from those frequencies, we're going to determine what the environment of the nuclei is. I want to talk very briefly about something called precession before I cut to a YouTube video that explains it a lot better than I could. Precession you can imagine as what happens to a spinning top when you exert a force on it from 90 degrees off its axis. Imagine that you've got a spinning top and the top is spinning perfectly on your desk. It's going to be aligned vertically, which is essentially in line with the Earth's gravitational field. As that top is spinning, if you flick the top from a 90-degree angle, so from the side horizontally, that top is going to wobble as long as you don't knock over the top. The top is going to wobble as it spins. That wobble is called precession. You can show here, like this nucleus, a ball, or the top spinning along its axis. If that axis is knocked off center, now so it's not aligned with the applied magnetic field, or in the case of a spinning top, the Earth's gravitational field, that axis will wobble around its kind of native precessional orbit axis. That's called precession as that wobbles. And we can actually observe that wobble in the nuclei. So the nuclei have spin, they are aligned with the magnetic field, and if we apply a pulse at 90 degrees from that magnetic field, they will wobble as a result of that, and we can watch that wobble because we can detect that movement of charge. As that nucleus wobbles, its charge moves, and that generates a signal that we can detect. And that frequency, the frequency at which that wobble occurs, is called the Larmor frequency. Now, I want to show you this video. I'm going to cut to it. If you want to watch it on your own, this is the link. This guy is going to explain precession in a very cool way. So hopefully that helped clarify what we're looking at. He showed two very important things. First of all, he showed that a spinning nucleus will align itself with an external magnetic field, the same way that the spinning wheel aligned itself with the Earth's gravitational field. The second thing he showed was that if you applied a pulse, a torque, that is to say, at 90 degrees from the axis of the spin and at the same frequency as the precession, you can cause the nuclei to wobble. So we are going to do that. We're going to apply a magnetic field, and then we're going to apply a force at a specific frequency. And that's going to be a 90-degree pulse of electromagnetic radiation at a certain frequency that's going to cause these nuclei to precess like that. And we can watch that wobble and determine from that what the environment is. Here are some pictures of nuclear magnetic resonance spectrometers that I took when I was at Yale in grad school in 2009. This is a 400 megahertz spectrometer. The megahertz rating is basically the precessional frequency of a bare proton. So that basically means that the higher that frequency is, the stronger the magnetic field. So you can see this 400 megahertz spectrometer is relatively small. It's about 8 feet tall. Here's some steps you can kind of see for scale. So you would take 2 steps up, you'd put your sample inside the slot here. The 600 megahertz is a bit taller. You can see that now we've got a step ladder to get up, and 800 megahertz is enormous. This is an enormous magnet in a very tall room. A 6'2" gentleman could stand approximately here. So this is maybe 15 feet tall. These are also extremely sensitive and expensive pieces of equipment. An 800 megahertz spectrometer costs upwards of $1 million. The schematic of an NMR is relatively simple. There are 2 magnets that are separated by a small distance. Those magnets have opposite poles, and between the 2 magnets, we put our sample in usually a little tiny spinning tube, and that it's called a spinning tube, and we put it in there, and the machine actually spins it, and as it spins it between a coiled radio frequency receiver and amplifier. So what happens is that we can put our sample in between the 2 magnets. That will generate the external magnetic field. We can spin our sample and apply the radio frequency to it. That applies our pulse, and then we can detect the frequencies that are absorbed and re-emitted, and that gets detected by a detector and gets recorded by a computer. Very simple physical setup. Now, I've been referencing that the amount of precession that we see is dependent upon the chemical environment. And that's because electrons that surround a nucleus can interact with the external magnetic field B0 as well. But the electrons interact with it in a manner opposite of the nucleus because they have opposite charges. So electrons will induce a magnetic field that is opposite to the nucleus's induced magnetic field, and that will minimize the effect of the applied magnetic field. Imagine that you have a nucleus that is surrounded by electrons. Those electrons will shield the nucleus from the external magnetic field, the same way that a heavy jacket would shield yourself from the blistering cold wind outside in winter. The higher the electron density around the nucleus, the more shielding you will see, and the less, or you can think of the lower percent of B0, the nucleus will feel. Lower electron density around the nucleus will have less shielding, and so the nucleus itself will feel more or a higher percent of the external magnetic field that we apply. This is called shielding or deshielding. And remember that the amount of magnetic field that you apply determines the difference in energy between the 2 spin states. So if we apply some B0, the difference in energy between the 2 states will be determined by how much shielding is around the nucleus. A bare nucleus would have no shielding, and so that nucleus would have the largest difference between the 2 states. But a nucleus with higher electron density around it will have more shielding, it will feel less magnetic field, and will have a smaller distance between its 2 states. That means that the frequencies that it will absorb in order to achieve resonance, and therefore in order to precess, will be different. So we can look at what frequencies cause precession, and from that determine what the chemical environment is. So here's methanol. Here's a molecule with 2 different types of hydrogens. We've got hydrogens on our carbon, 3 of them, and we've got a hydrogen on our oxygen, 1 of them. These 2 hydrogens are in very different chemical environments. The hydrogen on the oxygen is deshielded because the oxygen is withdrawing electron density from that nucleus. There's a polar bond there, and the more of the electron density sits at the oxygen, less of the electron density sits on the hydrogen. So we would say that the hydrogens on the carbon are more shielded, or we could say they are shielded, and the hydrogen on the oxygen is deshielded. And that means that these will achieve resonance at different frequencies or at different magnetic fields. You will need more magnetic field to get the hydrogens on the carbon into resonance because they are more shielded. You need to apply more magnetic field. The hydrogen on the oxygen will require less magnetic field because it has less electron density around it. So we say that these are high field protons, and these are going to be low field protons. The higher percentage of B0 is felt, higher energy is required for resonance. To give you kind of a visual description of this, here's a molecule that's 2 carbons. The carbon on the left has 3 hydrogens. The carbon on the right has 2 hydrogens and a bromine. So look at what the bromine does. Since the bromine is the most electronegative atom on our molecule, that's where all the electron density is going to sit. This carbon-bromine bond is going to be polarized so that the electron density sits over at the bromine. But that causes the carbon to pull electron density away from its hydrogens. These bonds, the carbon-hydrogen bonds, are going to be slightly polarized because of the presence of the bromine. That means that these hydrogens on the carbon on the right are going to feel a different amount of our applied magnetic field than these hydrogens on the left. Notice that these hydrogens on the left are not polarized. These electrons are sitting pretty much right in the middle of these bonds. They're not polarized. But these hydrogens have less electron density around them. So if we apply a magnetic field, let's say at 2.35 Tesla, that's a fairly common strength of magnetic field, 2.35 Tesla, neither of these nuclei are going to feel exactly 2.35 Tesla because all of these nuclei have electron density around them. But these hydrogens that are more shielded will feel much less than 2.35 Tesla. And these hydrogens that have less electron density around them only feel slightly less. So we might apply 2.35. These guys over here might feel 2.3. These guys over here might feel 2.34. Different chemical environments will determine the amount of shielding, which will determine the amount of magnetic field that they feel, and that will determine the energy that's required to get them to precess. It turns out that in an example like this, the difference in the effective magnetic field that these feel is only about 0.0000248 Tesla. A very, very, very small difference between the amount of magnetic field that these hydrogens feel versus what these hydrogens feel. That sometimes that is referred to as parts per million. This is 248 millionths, so 2.48 parts per million. We can talk about the difference in magnetic field that these nuclei feel in terms of ppm, parts per million. This is not a concentration. In general chemistry, you learn about ppm as being a measurement of concentration. That's also true. This is just kind of an abbreviation to refer to the difference in magnetic field in millionths of a Tesla. So this variation in resonance frequency that arises from these chemical effects is called the chemical shift. And this also means that the NMR requires an extremely uniform magnetic field. If our magnetic field varies at all, even as small as the distance between these two hydrogens, if these two hydrogens have a different magnetic field being applied to them, then their resonance frequencies are not going to accurately represent what their chemical environment really looks like. Or we could say what the difference in their chemical environment is really going to look like. So it's really important that these magnets are very, very, very uniform. They're extremely sensitive machines. All right, so again, I want to make this as clear as I can. If our spectrometer is listening at 100 megahertz, so we are looking at frequencies, resonance frequencies at 100 megahertz, so nuclei precessing at 100 megahertz, 100 million times a second, we would need to apply more magnetic field to overcome the shielding and get this nucleus to feel 2.35 Tesla. So maybe we need to apply 2.352 Tesla to get this nucleus to feel exactly 2.35 due to its shielding, and therefore precess at 100 megahertz so that we can hear it. Over here, we would need to apply less B0 than we did on the left to get this nucleus to feel 2.35 Tesla. So maybe we would need to apply 2.351 Tesla to get this guy to feel 2.35 Tesla, and therefore to precess at 100 megahertz so we can hear it. So there's two different things you can do. You can either listen at a single frequency and then scan across different magnetic field strengths and look for where you get resonance, or you can apply a single magnetic field and then apply a bunch of different pulses and listen at what comes back. Listen for what radio frequencies are absorbed and then re-emitted. Two different ways to perform an experiment like that. So there are many repercussions that arise from shielding or deshielding of the nuclei by their electronic environment. The first is that the number of different absorptions, or sometimes what we call signals or peaks, implies how many different types of protons we have. If we apply a magnetic field and we get 3 different radio frequencies being absorbed, that means that we have 3 different types of protons, or protons in 3 different types of chemical environments. So the number of signals that get absorbed tell us how many different types of protons we have. Remember when we looked at methanol, there were 2 different types of protons. There were the CH3 protons and there was the OH protons. So methanol would generate 2 different signals, one signal being generated by the shielded protons and one signal being generated by the deshielded proton. The amount of shielding indicated by the absorptions implies the structure near each type of proton. So the frequency at which they absorb tells us how much they are shielded. And therefore we can say, okay, this looks like methyl protons, or this looks like OH proton, for example. Other information that we will get from the NMR spectrum is that the intensity of the signal is correlated by how many protons of each type there are. So if a signal is very loud, that means that there are lots of protons absorbing and re-emitting those radio frequencies, which means that there are many types of protons that have that type of chemical environment around them. And lastly, we're going to talk about this in part 2 of NMR, is that the signals themselves will split into multiple signals, and the splitting pattern will tell us about nearby protons. So we'll talk about splitting in a little bit. But for now, let's look at a sample spectrum. Let's see what this actually looks like. So here's methanol again, and like we said before, methanol has 2 types of protons. There are the CH3 protons, and all of these 3 are identical. They're all in the exact same chemical environment. And then there's the OH proton, which is in a different chemical environment. And we said that because of the H's proximity to the oxygen, this hydrogen is going to be deshielded. The oxygen is going to be removing electron density from that hydrogen. That deshielding means that we need less magnetic field to get it to precess. The more shielded protons, the ones that are farther from the oxygen, have more electron density around them and therefore need more magnetic field to get them to precess. So here is what our graph looks like. This is what our spectrum looks like. This is plotted actually on the x-axis backwards from how we're used to reading a graph. This is plotted in order of decreasing B0 needed for resonance. So over here, we have high magnetic field required for resonance. And as we go to the left of our graph, we go down in the amount of magnetic field that we need. The alternate way to think about it is that if we have low magnetic field required, that means that these signals come from de-shielded protons. If they are de-shielded, that means they feel a significant amount of the external magnetic field, and therefore that their spin states will be very different in energy. So you can also think of this as increasing energy needed to achieve that resonance. We need to apply a greater frequency to correspond to that delta E between the two states. So either way, over here on the spectrum, on the right side of the spectrum, are these shielded protons. And as we go to the left, we get the de-shielded protons. That means less magnet required on the left and more energy required to get that delta E between the two spin states to be absorbed. So here are our two signals. We have one signal that requires more magnetic field. It's more shielded. That's the CH3 protons. And then we have another signal that is less shielded. It's de-shielded, and that is the OH proton. We call this upfield. The term upfield, higher field, is on the right, and downfield is to the left. You'll notice that these peaks are different sizes. Now, it's not the height of the peak that matters in NMR. In mass spec, you'll remember, the height of the peak tells us the frequency, how often those fragments are formed. In NMR, it's actually the area under the curve. That's called integration in mathematics. It's the area under the curve that tells us how many protons are generating that signal. So what this is telling us here is that the relative area under the curve, that is to say, the area under the curve of the big peak relative to the area under the curve of the small peak, is 3-to-1. There's 3 times the amount of area under the big peak than there is to the small peak, because there are 3 times as many hydrogens generating that signal as there are hydrogens generating our other signal. So 2 signals mean 2 different types of protons, or protons in 2 different chemical environments. We can see how shielded they are by how far left or right these peaks show up on our graph, and the area under the curve of those peaks, the integration of those peaks, tell us how many of each type of proton we have. That's a lot of information from a relatively simple graph. Now, you'll notice that there's another peak over here. This is called a reference peak, and this is just meant to give us a starting point, basically a 0 point, to show how far these 2 guys are from the reference peak. This reference peak comes by adding something called TMS, tetramethylsilane, to our mixture. The chemical shifts, that are to say, the distance that these peaks are separated from the reference peak, is called the chemical shift, how far downfield they are from this reference peak. TMS looks like this, tetramethylsilane, has basically the most shielded types of protons that you'll ever encounter in an organic molecule. These hydrogens on TMS are very, 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 very shielded. It's pretty uncommon to encounter hydrogens on any other organic molecule that are more shielded than TMS. So what you'll typically do is you'll put a little bit, a tiny drop of TMS into your sample before you take an NMR spectrum of it, and then your peaks will show up alongside the TMS peak. And since we know exactly where TMS should show up, everything else is measured relative to that TMS peak. We're going to say how far downfield in ppm are our signals from TMS. So the difference in parts per million between the resonance frequency of the proton being observed and that of TMS will give us what we call the chemical shift. It's the spectrometer frequency, how strong is the magnet, or how fast would our protons be processing in that magnet if it were bare protons shifted downfield from TMS. So TMS is going to show up somewhere, our bare protons would show up somewhere, and our actual protons are going to show up somewhere downfield from TMS. Spectrometer frequencies are typically fixed. For example, we could have a magnet that generates 60 megahertz by a bare proton, or 200 megahertz by a bare proton, all the way up to 800 megahertz by a bare proton. The higher the frequency of precession, the stronger the magnet. And remember, we want a strong magnet because that generates a bigger delta E between the two states, and therefore the transitions between those two states are easier to detect. Here are some numbers now. Here's our methanol spectrum again, with our methyl hydrogens more upfield and our hydroxy hydrogen more downfield. Again, it's de-shielded. There's less electron density around it, so it feels more magnetic field, which means that it needs less to be applied to get that frequency. Here's TMS, and again, we set TMS to be 0. That's going to be our baseline. Now, these methyl protons, that is to say, hydrogens that are on a carbon that is attached to an oxygen, typically fall in the range from 3 to 3.5. That is something that we know based on experiment, that hydrogens on a carbon that is next to an oxygen will show up between 3 and 3.5. And that's exactly where this peak shows up. We also know that alcohol hydrogens can show up anywhere between 2 and 5 ppm relative to TMS. That is a fairly large range, and that's because these hydrogens can participate in hydrogen bonding, and the amount of hydrogen bonding that they participate in is determined by the concentration of the solution. So because when a hydrogen bonds with another molecule, like an OH on another molecule, that will change its environment. And so its frequency that it absorbs will change depending on how much it is hydrogen bonding with other things in solution. And that is determined by concentration. So that's why we see a fairly large range for OH hydrogens. But anyway, they show up between 2 and 5. So that's what we see. We look at our graph and we see, okay, we've got something between 3 and 3.5. That's probably a methyl next to an O. And we've got something at 5 that's very likely to be a hydrogen on an O. We'll talk more about specific chemical shifts for specific groups in a little while. Let's look at the proximity effect for these chemical shifts. Here's butane, just C4H10, and the corresponding chemical shifts for these hydrogens. These methyls show up at about 0.9. The CH3s on the end show up at about 0.9 ppm relative to TMS. And these CH2s in the middle show up around 1.3 relative to TMS. Now, why would these be different? Notice that there's really no polarizing atom. There's nothing that's very electronegative like an oxygen that's going to remove electron density from these hydrogens. But actually, if you think about it, if you look on a periodic table, carbon is more electronegative than hydrogen. Carbon is about 2.5 on the Pauling scale for electronegativity, and hydrogen is about 2.1 on the Pauling scale for electronegativity. So These hydrogens that are secondary on secondary carbons are surrounded by more carbons than the primary hydrogens are. So these guys in the middle are actually being deshielded because they're closer to more carbons. That effect is really small. We would never consider these secondary carbon-hydrogen bonds to be polar bonds, but they are very slightly more polar than the CH3 bonds are because of the fact that a carbon is very, very slightly more electronegative than hydrogen. So we can actually see that effect in NMR. It's a very, very, very subtle effect. But anyway, they're around 0.9 to 1, say maybe from 0.9 to 1.3, 1.4 for normal hydrogens on butane. But look what happens when we put a bromine on that. For one bromobutane, all of a sudden, the hydrogens on our first carbon, we're going to call this the alpha carbon because it is the first position next to the bromine, our alpha hydrogens shift to 3.4 ppm relative to TMS. So they go downfield because they're being deshielded by that bromine. Our beta hydrogens also shift. They shift to 1.7. Again, because they are in close proximity to this bromine, which is deshielding. The bromine deshields the carbon, which deshields the hydrogens. This carbon then deshields its neighbor, which deshields its hydrogens. But notice that once we get to the third carbon, our gamma carbon, those hydrogens are exactly at the same shift that they were before. They were 1.3, regardless of whether the bromine was there or not. And on our delta carbon, our fourth position over, our hydrogens are at 0.9, which is exactly where they were before we had the bromine on there. So we can see the deshielding that results from the bromine in ppm. Our alpha hydrogens are deshielded by 2.5 relative to where they were before. Our beta hydrogens are deshielded by 0.4 relative to where they were before, 1.3 to 1.7. But beyond that, we have no deshielding. So strongly deshielding atoms, that is to say, atoms that are very electronegative and will pull electron density away from their neighbors, for example, bromine, chlorine, and oxygen, will affect protons up to 1 or 2 carbons away, but not beyond that. So we can kind of infer from our observed chemical shifts how far our groups are from a deshielding atom. You can see here the electronegativity of these atoms or groups. Iodine is 2.7, bromine is 3, chlorine is 3.2, oxygen is 3.4, fluorine is 4, and therefore the chemical shift of the hydrogens that are on a carbon that has the X. So here we showed that hydrogens on the carbon bearing the bromine were shifted to 2.5. Here they show that the shift is around 2.7. An iodine would shift them to 2.2. A chlorine would shift them 3. A OH oxygen would shift them 3.4. And a fluorine would shift them 4.3. This is kind of cool because the shift of those alpha hydrogens are approximately the same as the electronegativity on the Pauling scale. That's not a coincidence, by the way. Okay, so here is a great table from the Wade textbook that shows you common shifts for common functional groups. That is to say, these are where the protons show up relative to TMS on a NMR spectrum. We showed that methyl hydrogens absorb around 0.9. That's what we showed over here. Our methyls were around 0.9. Those are primary hydrogens. Secondary hydrogens show up at about 1.3. That's what we saw here. The secondaries were about 1.3. Tertiaries show up at about 1.4. So all of these are very shielded, but NMR actually lets us differentiate between methyls or primaries, secondaries, and tertiaries. That's pretty cool. The very slight change in chemical environment from a primary to a secondary to a tertiary hydrogen can actually be observed in NMR. Hydrogens on a carbon adjacent to a carbonyl shift 2.1. We call that, say, a methyl ketone functional group. Shows up at 2.1. That's a very common shift. Acetylenic hydrogens, so hydrogens on acetylene, show up at about 2.5. Hydrogens that are alpha to a halogen or an oxygen, we saw showed up around 3.4. Iodine is a little bit lower than that, but generally speaking, halogens or oxygens will shift around 3 to 4. Vinyl hydrogens shift 5 to 6. Allylic hydrogens shift 1.7. Aromatic hydrogens that are, say, hydrogens on a phenyl ring or on a benzene ring shift to 7.2. If they are benzylic, if they are on a carbon that is attached to a benzene ring, they're benzylic on the benzylic position, they shift to 2.3. Aldehyde hydrogens are 9 to 10. Carboxylic acid hydrogen is 10 to 12. Alcohols, whether they are aliphatic, so on a normal R group, or aromatic, so on an aryl group, they can be variable, but aliphatic alcohols we showed are about 2 to 5. Aromatic alcohols are going to be about 4 to 7. And amines, hydrogens on the nitrogen, are going to be from 1.5 to 4. Now, some of these are very obvious. The methyl hydrogens or the alkyl hydrogens, these guys make sense why they will be very shielded because they are on carbons which are not particularly electronegative. As we increase proximity to an electronegative atom or group, for example, next to a carbonyl or next to a halogen or an oxygen, or again, on an aldehyde on a carbonyl, or on an acid, or on an alcohol, or on a nitrogen, those get more deshielded. Those numbers get higher from 2.1 to 3 to 4, all the way to 9 to 10 or 10 to 12, or somewhere in between for alcohols and amines, 2 to 5, 4 to 7, 1.5 to 4. Makes sense why those would be deshielded because they are close to electronegative atoms or groups. But there are some weird things going on here. The ones basically that I've highlighted here, the vinyl hydrogens, hydrogen on a double bond carbon, or hydrogens on an aromatic ring, those are really high. They look like they are being deshielded all the way 5 to 6 or to 7.2. That's very close to an aldehyde, but there's no electronegative group here. So there's something weird going on here, and I want to show you what that is. It's something called diamagnetic anisotropy. That's a very technical, fancy word for something that's actually kind of simple. Remember that in a benzene ring, we've got this conjugated aromatic system that allows the electrons to move around the ring. That conjugated system of all these overlapping p orbitals allows electrons to move around the ring. And remember, we showed that when you have movement of charge, like when you have a spinning nucleus or a loop of current, that will generate a magnetic field. And the electrons in benzene, or a conjugated system, an aromatic system, that have electrons moving around the ring, the circulation of those electrons generates their own magnetic field. And you'll notice that since these electrons are moving in an external magnetic field, their magnetic fields will interact. And that means that the hydrogens on the benzene ring will not only feel the external magnetic field, but they will also feel the magnetic field that is generated by the moving electrons in the ring. That means that these hydrogens on our aromatic ring feel more magnetic field than they should. Now, think about what I just said. If an atom feels more magnetic field, that's like it's being deshielded. The whole reason why our methanol OH hydrogen was downfield, had a higher shift, is because it is being deshielded by the oxygen. This hydrogen feels a lot of magnetic field because it is being deshielded by the oxygen. So these hydrogens feel a lot of magnetic field as well, but it's not because they're being deshielded. It's because they are actually literally feeling more magnetic field because there is more magnetic field around them. We not only have the applied magnetic field, we have the ring current magnetic field. That is called anisotropy. We call it diamagnetic anisotropy because this comes from aromatic systems where all of the electrons are paired. And you might remember from general chemistry that a system that has all the electrons paired is called a diamagnetic system. So this is called diamagnetic anisotropy, and it is why we see the hydrogens on aromatic systems or in otherwise hydrogens near other pi systems like the C double bond C or the C triple bond C in acetylene be downfield farther than we would expect. They are not downfield as a result of being deshielded. They are downfield as a result of feeling additional magnetic field adjacent to them. So I want you to learn these shifts. I'm going to show you a slide towards the end of this lecture that shows that these are not really that difficult to memorize. But I do want you to know what primary, secondary, and tertiary hydrogens shift to, or what a methyl ketone shift is, or what an alpha hydrogen shift is, or what a aldehyde or acid or alcohol or phenol shift looks like, or what an aromatic shift looks like. I want you to know these numbers. I want you to be able to look at an NMR spectrum and from our shifts determine what types of hydrogens we have present. This is methylbenzene, also known as toluene. So it's a benzene ring with a methyl group on it. Now, we have two types of hydrogens here. We have the methyl hydrogens, and we have the hydrogens on the benzene ring. So two different types of hydrogens means two different chemical environments, which means we should have two different signals on our spectrum. And indeed we do. We have our aromatic signal, which is this big jumbled mess around 7.2. I'm going to show you in a minute why it's a jumbled spectrum. But looking at our table here, aromatic hydrogens show up at 7.2. So that signal at 7.2 is a sign that we have hydrogens on an aromatic ring. It doesn't necessarily tell us how many at this point, but we can at least determine that we do have hydrogens on that ring. Then we have these methyl hydrogens. Now, these methyl hydrogens are not normal methyl hydrogens. Normal methyl hydrogens would show up at 0.9, like we saw here. Regular methyls will be at 0.9, or like we saw here, regular methyls will be at 0.9. These are not normal methyl hydrogens. What is not normal about them is that they are on a ring. They are on a carbon that is on a benzene ring. They have a close proximity to the diamagnetic anisotropy of the ring, and that pulls it downfield a little bit. These methyls are feeling a little bit more magnetic field than they normally would. So they need less to be applied for them to get into resonance. So those who would say they're benzylic, those hydrogens are on the benzylic position. And here we see that benzylic hydrogens show up at around 2.3. That's pretty close to what we have. This looks like it's about 2.4, but very, very, very close. These anisotropic benzene hydrogens should show up at 7.2, and the methyl H's expected to be at 0.9 show up at 2.3 on account of being near the benzene ring. The benzene ring effectively deshields groups that are near it. Now, if you think about these hydrogens on the ring, it would make sense to say that these hydrogens here and here are in a different environment than the hydrogens here and here, and everything is in a different environment than this last hydrogen here because of their proximity to the methyl group, right? These guys are 1 carbon removed from the methyl. These are 2 carbons removed from the methyl. This guy is 3 carbons removed from the methyl. So we should really have 1 signal from the methyl hydrogens, but then a second signal from the adjacent hydrogens, a third signal from the hydrogens 1 carbon further, and a 4th signal from the last hydrogen. So that is why we get the jumbled mess here, because really this is 3 different signals. It's the hydrogens that are closest to the methyl, the hydrogens that are farther from the methyl, and the hydrogen that is farthest from the methyl. The only thing is that the ring is such an overpowering effect on the environment that the distance from the methyl makes very, very, very little difference in the chemical shift. So you end up typically with a big jumbled mess when you have aromatic hydrogens like this. So treat that as 1 signal. It's really very complex because there's a lot going on here, but for the most part, that's what you're going to see from hydrogens on a benzene ring. Here's acetic acid, another molecule with 2 types of hydrogens. We've got hydrogens on the carbon that's adjacent to the carbonyl, and then we've got the hydrogen on the oxygen that's adjacent to the carbonyl. Now, so 2 different types of hydrogens, very clearly in different chemical environments. Based on our table, the shifts should make sense. Remember, these are the methyl ketone hydrogens. We showed you that right here. Hydrogens on a carbon adjacent to a carbonyl show up at 2.1. So these guys on a carbon adjacent to a carbonyl, the methyl ketones, should show up at about 2.1. That's exactly where they show up. The hydrogen on the carboxylic acid, that shows up from 10 to 12, somewhere between 10 and 12. And here they go up to 10 on our scale, and then it shows a peak and it says offset 2.0 ppm. That means that it is 2 ppm beyond our graph. So that is 12. That is the signal there. Now, the integration of these signals, you can see that the single hydrogen over here gets a tiny signal, and the 3 hydrogens over here get a much larger signal. If you were to calculate the area under these curves, the area under the 2.1 curve would be 3 times greater than the area under the 12.0 curve. So here's methyl T-butyl ether. We've got an ether with a methyl on one side, a T-butyl on the other. We've got 9 hydrogens that are all identical on the T-butyl group. These 3 hydrogens are identical to these 3 hydrogens, which are identical to these 3 hydrogens. So we've got a big peak, but those are going to pretty much be shielded. They are 2 carbons separated from the O on the ether. So normally these methyls, we'd expect them to be around 0.9, but you can see here they're about 1.2. We can explain that shift by being in relatively close proximity to a deshielding atom. Then we've got these methyl hydrogens over here. Again, normally methyls are going to be at 0.9, but if they are close to a very electronegative atom, it's going to shift further, and these shift all the way to 3.2. Again, you can go back and look at this chart to tell you how far they're going to shift. If they are on the carbon that's attached to our electronegative atom, if it's an OH, it's going to shift 3.4 from TMS. That's exactly what we see here. It's shifting 3.3 from TMS. If we integrate this, we have 3 hydrogens in our 3.2 peak, and we have 9 hydrogens in our 1.2 peak. So the integration should be 1 to 3. We should have 3 times more area under the big curve than the small curve. Now, if you look carefully at this graph on the bottom, you'll see this blue line that goes horizontally, and it gets higher and higher and higher and higher. And then when it hits our first peak, notice that it jumps. That blue line goes vertical, and then it goes horizontal again, horizontal again, horizontal again, and then it goes vertical again when it gets to our next peak, and then it goes horizontal again, again, again. So that is what we call the integration line. The graph will plot this line, and based on how this line's height increases, that tells us what the area under the curve is. Notice that the vertical jump at our first peak is approximately 2 spaces. It started at this first line and it jumped up to the 2 lines above it. That's 2 spaces. And then when it got to our next peak, it jumped 6 spaces. 1, 2, 3, 4, 5, 6. 6 spaces. So 2 spaces for our first peak, 6 spaces for our next peak. That's 1 to 3. That's a 1 to 3 ratio. It's the ratio that matters. 2 spaces does not necessarily mean 2 hydrogens. 6 spaces does not necessarily mean 6 hydrogens. But 2 spaces to 6 spaces is 1 to 3. That is the same ratio as 3 to 9. So it's the ratio that matters. That's called the integration line. And again, that's another piece of information that the spectrum will give you. Here's another example. T-butyl 3-oxobutanoate. This is an ester, but we've got 3 different types of hydrogens. We've got these T-butyl hydrogens on these methyls. And remember, that looks exactly like what we saw before, the T-butyl group next to an oxygen, with these hydrogens being 2 carbons removed from that oxygen. They should shift from about 0.9 to about 1.4. This looks like about 1.5. The reason this might be a little bit higher in the shift is because there's also a carbonyl there. So we've got 2 electronegative groups here instead of 1 like we saw before. So we've got hydrogens type A, we've got hydrogens type B, and we've got hydrogens type C. Now, as far as where their shifts should go, notice that B looks like a methyl ketone. These guys are on a carbon adjacent to a carbonyl, and we said that that should be about 2.1. Here it's about 2.2 or 2.3. But again, that's also because we've got more electronegative groups over here as well. So they should be maybe a little bit more downfield than we would normally expect. These 2 hydrogens in the middle, notice that hydrogen C here are between the 2 carbonyls. They are kind of doubly methyl ketone. They're methyl ketones relative to our first carbonyl over here on the left, and also from our ester group on the right. So they should be the most deshielded. They are in closest proximity to withdrawing groups. And then lastly, the hydrogens that are farthest from withdrawing groups are our methyl hydrogens. And so they would normally be at about 0.9, but because they're next to the O and the carbonyl, they're going to shift to about 1.4, 1.5. Their integrations, we've got 9 type A's, we've got 3 type B's, and we've got 2 type C's. So we would expect a ratio of 1 for the C's to 1.5 for the B's to 4.5 for the A's. Here's another example. This is 4-hydroxy-4-methyl-2-pentanone. Again, we've got 3 types of hydrogens here. We've got hydrogens type A, which are on the methyls, here and here. Or we've got 4 types, We've got the 2 methyls, type A. We've got the methyl ketones, those are type B. We've got the hydroxy hydrogen, that's type D. And then we've got these 2 hydrogens in between, which are going to be type C. Now, thinking about where these should shift, remember our OH should be the most deshielded. This H is closest to the oxygen, closest to a deshielding group. And we said that those show up between 2 and 5, depending on our concentration. So here's something at just below 4. That should be our D peak. Our most shielded, our farthest from our electronegative groups, are type A hydrogens, our methyls. The normal methyl hydrogen should be around 0.9, but notice that they are on a carbon that's next to a carbon that's next to an oxygen. So there's going to be a little bit of deshielding from that oxygen. So that's why our A shows up a little bit over 1 instead of about 0.9. Now we've got to choose between our B and our C. Notice that they are both methyl ketones. Their default position should be about 2.1. But notice that these are different. The C hydrogens are closer to this oxygen over here than our B hydrogens are. So these are both in proximity to the ketone, and that's what's going to put them at 2. But our C's are going to be pulled a little bit more downfield because they're closer to our oxygen. So our A should be the lowest, and that's our biggest peak because there's 6 of them. Then we're going to have our B's, which are going to be about 2.1. That's what we see here. It's about 2.2. That's fine. Then our C's are going to come next. That's going to come next, and see that they're at about 2.6 or 2.7. So that must be caused by the proximity to our oxygen. And then lastly, our D hydrogen is going to be at a little bit before 4. Now, look at the integration line. If we follow this blue line, it jumps about half a space on our first peak. It goes about a full space to half spaces for our next peak. Then it goes up 1.5, so 3 halves for our next peak. And then it goes up 3 whole spaces or 6 halves for our next peak for our A. So our integrations are 0.5, 1, 1.5, and 3. If we make those whole numbers, it's 1 to 2 to 3 to 6. So those whole number ratios are actually the exact integrations of our peaks. D is 1 hydrogen. C is 2 hydrogens. B is 3 hydrogens. And A is 6 hydrogens. So again, the integration gives us the ratios. And a lot of times we can infer from those ratios what the actual numbers would be, the actual quantities of those hydrogens would be. So let's think about what information this graph communicates. Remember, we said there's a lot of information that NMR will tell us. The first thing is that we see 4 signals: signal A, signal B, signal C, and signal D. 4 signals means 4 different types of hydrogens, or hydrogens in 4 different chemical environments. And that's already been labeled for us. Our methyls are the same. Those are in one environment. Our hydrogen on our oxygen is another environment. Our CH2s are another environment. And our CH3 over here is another environment. So 4 different chemical environments means from 4 different signals. We've got integrations, which tell us how many hydrogens are in each environment. From our integration, we can infer that we've got 1 hydrogen in our D environment, 2 hydrogens in our C environment, 3 hydrogens in our B environment, and 6 hydrogens in our A environment. Then we can look at the chemical shifts. And from that, we can figure out what those environments might be, or generally speaking, where they might show up. We can infer that A's are probably methyls or something close to methyls. We can infer that B's are something like methyl ketones or close to methyl ketones. Something up here around 4 to 5 is likely a hydrogen next to an oxygen or next to a halogen. Since it's only 1, it only integrates to 1, that's really easy to kind of guess that it's a single hydrogen on an oxygen. And then C could be really anything. It's kind of hard to tell in this area whether this is next to an oxygen or a halogen, or whether it's a shifted methyl ketone, which it actually is. It's a shifted methyl ketone. Or if maybe it's an alcohol that's showing up between 2 and 5, and it's just on the lower end of that. There is some ambiguity, but at least we have a good sense of what those environments are likely to be. So let's do a quick quiz. Let's match the spectrum to the structure that we have here. We've got 6 structures to choose from. Let's determine which structure is most likely to be represented by this spectrum. Now, where I would start, first of all, our peak at 0, that's TMS. So we can ignore that. So all our other peaks are what are being generated by our molecule. So we've got 3 peaks here. And remember, 3 different peaks means 3 different chemical environments. So our molecule that we choose needs to have hydrogens in 3 different chemical environments. By the way, we can rule out all 3 of these ring structures because all 3 of these ring structures have hydrogens on the ring. And remember that aromatic hydrogens on a benzene ring, should show up at around 7. And we have no hydrogens showing up at around 7.2. So right off the bat, we can rule out these ring structures. So that leaves us with these linear structures here. Let's try to find one of these structures or a couple of these structures that has 3 different types of hydrogens. Let's look at this guy here on the right. These methyls, CH3, are the same as these methyls, the CH3. They are both on the same carbon. So those are one type of hydrogen. Then we've got these 2 hydrogens that are on the same carbon. So that's another type of hydrogen. So this only has 2 types of hydrogens. So this should only generate 2 signals. How about over here? We've got these CH3s and we've got these CH3s, but those are different because these CH3s on the left are closer to the bromine. So we've actually got 4 signals here. We've got the CH3 next to the bromine. We've got the H on the carbon with the bromine. We've got the 2 hydrogens adjacent to the carbon with the bromine. And we've got these hydrogens way over here. These 3 over here should be very similar to these 2 over here because of their proximity to the bromine. But these guys are got a methyl group on them. So that's going to change their environment. So we've got 4 different environments here. And we've only got 3 signals on our graph. So that doesn't work either, which means that this one better work. And indeed it does. You can see that these CH3s and these CH3s are in the same environment. They're attached to the same carbon. So that's going to be one type. We've got our H on our oxygen. That's another type. And then we've got our acetylenylic hydrogen. That's another type. Now, let's try to figure out which hydrogens correspond to which of these peaks. Which one should be the most downfield, the most de-shielded? Well, it should be the hydrogen on the oxygen. If we go back and look at our table with all of our chemical shifts, alcohol hydrogens on an O, like we saw, should be around between 2 and 5. Acetylenylic hydrogens do not have much of a range. They should be around 2.5. And then methyls start at 0.9 and can be shifted downfield based on their proximity to other groups. So let's try to apply those numbers to what we have. We've got something right at 2.5, smack dab between 2 and 3 ppm. That is our acetylenylic hydrogen. So this peak right there is our acetylenylic hydrogen. That's 1. Our higher shift then must be our alcohol. Remember, the alcohol can show up between 2 and 5. And since this one's right at 2.5, that's a good guess for our acetylene. That leaves this other peak for our alcohol. Then we've got this lower peak that's at 1.5. Now remember that methyls should be 0.9, but these methyls are on a carbon that has an oxygen. So this oxygen is deshielding these methyls just a little bit to pull it from 0.9 up to 1.5. Let's look at the integration. You can kind of see this blue line jumps approximately the same distance on our first peak as it does for our second peak. Notice it's about the size of my mouse cursor. Jumps one mouse cursor size there and another mouse cursor size there. That means that our peak from 2.5 is the same as our peak in terms of integration as our peak at 2.7. Our acetylenic hydrogen is 1 and our alcohol hydrogen is 1. So those should have the same integration, and indeed they do. Our other methyls, there's 6 of them. So these integrations should be 6 times what our other integrations are. So it should be about 6 mouse cursors. We can maybe go 1, 2, 3, 4, 5, 6, pretty close to 6. So that makes sense. Our big integration should be our methyls, the lowest, most upfield peak. Then we have a 2.5 integrating to 1. That's clearly our acetylene. And we've got something higher than that integrating to 1, which is clearly our alcohol. Now, the last piece of information that NMR tells us is something that comes from what we call spin-spin splitting. And this is really where NMR gets interesting. Spin-spin splitting tells us what is next to each type of hydrogen. This is very, very cool. This is a very interesting looking structure. Now, here we've got 2 carbons. One carbon's got 2 bromines and a hydrogen. The other carbon has 1 bromine and 2 hydrogens. So we've got 2 types of hydrogens, hydrogen A and hydrogen B. So we've got 2 different chemical environments. Therefore, we should have 2 peaks. Now, the hydrogen that's on the carbon with 2 bromines is more deshielded than the hydrogens that are on the carbon with 1 bromine. So we would expect our hydrogen A to be downfield and hydrogen B to be upfield. So we've got 2 peaks and we can determine which hydrogens are causing which peak. But notice that hydrogen A is not a single peak. It actually gets split into a triplet, 3 peaks, which we call a triplet. And hydrogen B is not a single peak, but rather it gets split into 2, which we call a doublet. Now, 2 hydrogens showing up as a doublet, that might make sense. The doublet means 2 hydrogens. But we've got 1 hydrogen that's being split into 3. So that's clearly not the relationship. How it splits, it turns out, does not depend on the hydrogen, but rather it depends on the neighboring hydrogens. So let's look at what's going on here. This is actually quite complex, but in reality, at the end of the day, it ends up being very simple. So let's look at our molecule and imagine that our molecule is in an external magnetic field, B0, that's say pointing in the up direction. Let's consider an HB looking at HA. Imagine that our HB can feel its neighbor. Now, what do I mean by feel the neighbor? Well, hydrogen A has its own magnetic field. Remember, it's a proton, that it has a nucleus that's a proton that is spinning, and therefore it generates its own magnetic field. Hydrogen A can be aligned with the external magnetic field, so aligned up, or it can be aligned against the magnetic field, so pointing down, meaning hydrogen can be in an alpha state or a beta state. Now, like we said, usually it's going to be in the alpha state because alpha state is much better than beta state. Being aligned with the magnetic field is better than being aligned anti-parallel to the magnetic field. But either way, hydrogen A could be up or down relative to the external magnetic field. And hydrogen B can feel that. So we're going to imagine that we are a hydrogen B and we are feeling hydrogen A. Now I want to point out that all hydrogen Bs will behave identically with respect to HA. These are indistinguishable protons. They're indistinguishable from one another. So they're going to both kind of show up in the same way on the spectrum. So hydrogen B should have a chemical shift associated with it. Let's say the shift is there. I'm just going to draw a line to say where the shift is. Now, let's say that hydrogen B feels hydrogen A with A spinning with the magnetic field, so aligned with the magnetic field. That means that B feels the external magnetic field plus A's magnetic field aligning with it. That means that it's going to shift a little bit downfield from where we would expect HB feeling HA aligned up. But HA could also be down. And if HA is down, that's going to oppose the external magnetic field and kind of cancel it out, which means that B's are going to feel the external magnetic field minus A's magnetic field. And so it's going to shift a little bit upfield. So B is actually going to split into two signals. One signal for when it feels A up, and another signal for when it feels A down. It turns out that the difference between those two peaks is 7 hertz. The difference in precession frequency from when B feels A up versus when B feels A down is about 7 hertz. That's the effect that A's magnetic field has on B's precession frequency. So B does not show up as one peak. It shows up as 2 peaks because it either feels the magnetic field plus A or the magnetic field minus A. 2 peaks. That's what we call the doublet. Remember that when we looked at our spectrum, B was more downfield because it's closer to only one bromine. That's a doublet. That doublet is from feeling A up and feeling A down. So A reinforcing the magnetic field or A opposing the magnetic field. Basically, the doublet implies that the B's are next to one hydrogen. That hydrogen could be up or down. So B feels A, which can either be in the alpha state or the beta state. The alpha state reinforces the magnetic field, causing B to shift downfield. Remember that when an atom feels more magnetic field than it should, it shifts downfield. When it feels less magnetic field than it should, it shifts upfield. So the beta state that opposes B0 causes B to shift upfield. That is the origin of our doublet. Now, let's figure out where we're getting this triplet from. Let's imagine A feels B, or A looking at B. Here's A's expected shift. Let's say some arbitrary point. A can feel its neighbor B up, or it can feel its neighbor B down. Again, B is going to either reinforce A, or B is going to cancel out the magnetic field with A. So that's our doublet, but it's not a doublet because we not only feeling one B, A is going to feel the other B as well, which means that A can feel both of the B's pointing up, or it can feel one B up and one B down. Now, if that's the case, the B that's aligned with the magnetic field adds to it, and the B that is aligned against the magnetic field cancels that out, which means that this signal is exactly where we would have expected A to be if it did not feel any of its neighbors. One is aligning with, one's aligning against. That's no net effect. The other signal, though, B down, if we added a B up from it, would also get us that same signal back. B down and then B up. Or we could have both B's down. So we've got 3 different possibilities. A feels B up up, up down, down up, which is the same, or down down. So that's 3 peaks. That's our triplet. And notice that our ratio is there's one opportunity for up, up. There's one opportunity for down, down. There's two opportunities for up, down, and down, up, which are the same. So we don't get two equal peaks or three equal peaks. We get three peaks at a 1 to 2 to 1 ratio. That is what our triplet looks like. This triplet indicates that HA is next to two hydrogens. There's our triplet. It's a 1 to 2 to 1 ratio because of the number of possibilities for these spin combinations. Let's go back and look at our spectrum again. The B's are next to 1. That 1 can be up or down, so they're going to split into a doublet. The A is next to 2, which can be up, 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 down, down, up, which is the same as up, down, or down, down. So we've got up, up, down, and down, up, and then down, down. 3 different possibilities means that it splits into a triplet. Let's look at an example where we have H next to 3 H's. So again, we've got the blues that are next to 3 H's. Let's imagine what's going to happen here. Each H could be up or down. Each red H could be up or down. So here's the expected shift of our blue H. Let's say that H feels a neighbor in the up orientation. That's going to reinforce the magnetic field and shift our signal down field. We could also feel that neighbor down, which means that it's going to cancel out some of the magnetic field and it's going to shift us up field from where we might expect. That's the effect of one neighbor. Now, let's add in the effect of another neighbor. We can have up, up, which is going to doubly reinforce. We can have up, down, so up and then down, which is going to take us down field and then up field and put us back exactly where we would have started. We could also feel down, up, which would give us also, we're going to go down and then up. That's also going to put us back to where we started. And then we could also feel down, down, which is going to doubly cancel out our magnetic field. So that's what we look like with the triplet. We've got 1 to 2 to 1, 3 signals. That's a triplet from being next to 2. But we've got a third neighbor here. So we're going to add our third neighbor in again to this. So we could have up, 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 or up, up, down. So we're going to go up 1 notch, and then up 1 notch, or up 1 notch, and then down 1 notch. We could also have the up, up, down, up, or the down, up, up. So we can go up, up, down, or up, down, up, or up, down, down. That's another peak in there. We can keep going. Add our third guy in. We could have down, down, up. So go down, down, up. Or we can also go down, down, down. So these are all the combinations of ways that we can have 3 spins aligned. Up, 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 down, 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 and then 2 up and 1 down. So up, up, down, up, or down, up, or 2 down and 1 up. So down, 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 or down, down, up. How many peaks do we have? We have 4. We call this a quartet. But the quartet is not in a 1-to-1 ratio like the doublet was, and it's not in a 1 to 2 to 1 ratio like the triplet was. It's in a 1 to 3 to 3 to 1 ratio. So it's different as well. What we end up with are 4 signals at 1 to 3 to 3 to 1 intensity. We call this the N+1 rule, meaning that if a hydrogen is next to 0, if it's next to none, it's going to be a singlet. If the neighbor is 1, we have one neighbor. That neighbor could be up or down. That's where we got our doublet, and they were in a 1-to-1 ratio. When we had 2 neighbors, we got the triplet, which was up, up, down, down, and then up, down, and down, up, which were the same. So there's 3 possibilities, and they were in a 1-to-2-to-1 ratio. When we got 3 neighbors, it split into a quartet, and those were at 1-to-3 to 3-to-1 ratio. This is Pascal's triangle, where you take ones along the sides, and you say 1 plus 1 makes 2, 2 plus 1 makes 3, 3 plus 1 makes 4, 4 plus 1 makes 5, and you fill in all of these sums, you get this pattern. The ratios that we observe in NMR, from the singlet to the doublet to the triplet to the quartet, and beyond that we can have a quintet or a sextet or a septet, the ratios of those multiple peaks follow Pascal's triangle. A doublet is a 1-to-1 ratio. A triplet is a 1-to-2-to-1 ratio. A quartet is a 1-to-3 to 3-to-1 ratio. A quintet would be a 1-to-4 to 6 to 4-to-1 ratio. If you go and figure out all the ways that you could have 4 spins aligned from 4 neighbors, up, 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 down, 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 and all the combinations thereof, you have 1-to-4 to 6 to 4-to-1. So we call this the n plus 1 rule, because if it's next to n neighbors, it will split into n plus 1 peaks. 0 neighbors is a singlet, 1 neighbor is a doublet, 2 neighbors a triplet, 3 neighbors a quartet, etc. Hydrogens must be adjacent through bonding to split, meaning they have to be vicinal. They have to be on neighboring carbons. If they are farther than that, if they are separated by an atom or 2, they will not split. They have to be neighbors in order to split. They have to be near each other. They have to feel each other, right? The splitting comes from feeling their neighbors' individual magnetic fields. And the n plus 1 rule only works when all splitting distances are equal. What I mean by that is, if we look at the splitting tree for a quartet, notice that all of these distances are 7 hertz. The distance that one of these neighbors adds or subtracts to the precession frequency of our blue hydrogens are always 7 hertz. And that fact that they're always equal means that they overlap appropriately. And that overlap causes our signals to be at those ratios. So if for some reason these distances are different than 7 hertz, if one's 7 hertz, one's 11 hertz, one's 15 hertz, for example, we're not going to get this n plus 1 rule in effect. Now, these distances that I'm referencing that all have to be equal in order for the n plus 1 rule to work are called coupling constants. And different relationships between different neighbors have different coupling constants. Coupling constants, we give it the variable J. But here I'm showing you that if we have neighboring hydrogens, say on sp3 carbons, like we have here, in this structure we've got sp3 hydrogens here and sp3 hydrogens here. They're sp3 neighbors. That relationship looks just like this. sp3 neighbors. Their coupling constant is around 7. It can vary very slightly from 6 to 8, but usually it's about equal to 7 hertz. But if you are related as neighbors differently, say instead of being sp3 neighbors, if you're sp2 neighbors, you would have different constants, different coupling constants, different distances between your splits. For example, cis alkene neighbors, hydrogens that are neighboring on an alkene in a cis relationship, their distance will typically be somewhere between 7 and 12 hertz. If you are trans alkene neighbors, you will split as 13 to 18 hertz. And usually it's right in between. So usually this would be around 9 hertz. Usually this would be around 15 hertz. If you are neighboring as sp3 to an sp2 like this, your splitting will be very small, only 1 to 3 hertz. If you are neighboring on a benzene ring, that's 6 to 9 hertz. That's very similar to what it looks like here. This is basically a cis double bond neighboring. That should be very similar to what we see here. I said this is usually about 9. This is about 6 to 9 here. And if you are on a hydrogen on an alcohol next to a sp3 neighbor, you can have as little as 0 splitting, meaning that technically this HA is a neighbor to this HX over here. But sometimes you get no splitting. In fact, when we looked at methanol, this H technically should split with these H's because they're neighbors. H's are on this carbon. The blue H is on the carbon's neighbor. So technically this H should split with these into a quartet. But because of the fact that it's an alcohol, in methanol, we're actually getting 0 hertz splitting. It's fairly uncommon for alcohols to split. They usually sit at 0 hertz, so you only end up with a singlet. But under strange circumstances, usually at very, very, very high concentrations, you do get splitting. I have several slides here with different coupling constants showing different relationships between different neighbors. So here we have hydrogens that are not on neighbors. We've got hydrogens on a carbon that are separated by some number of carbons to finally another carbon with a hydrogen. There should be 0 splitting between those guys, unless you have some very strange orientation that places these H's near each other so that they can actually feel each other. Like if they are, say, bent over and kind of crisscross so that they're kind of in close contact with each other, then you might get splitting. But generally speaking, as long as this is a non-rigid molecule, these H's are going to be way too far away from each other to feel each other. So there's going to be 0 splitting. sp3 neighbors are usually 7. That's a pretty good guess. Here's more sp3 neighbors. But if you have certain dihedral restrictions, for example, if X and Y force the H's to be very close or to be very far, they can vary from 2 to 12 hertz. We saw that sp3 to sp2 neighbors could be around, say, 1 to 3. This slide says 5 to 3. If you have what we call diastereotopic hydrogens, meaning hydrogens that are different because of a chiral carbon, they can actually split each other, and they can split from 12 to 15. So I've got all these slides here. I've got 1, 2, 3 slides with different coupling constants. That it's something that we want to take into account. If you're looking at a structure, don't always assume that the n+1 rule applies. The n+1 rule only applies if all of the hydrogens in the splitting have the same coupling constant, which is usually around 7. But if they involve sp2 hydrogens or there's some chirality going on, check these slides to make sure that they don't have different coupling constants. And I'm going to show you in a minute what we do to compensate for that. A couple other features about NMR involving spin-spin splitting is that peaks that are related to one another often lean into one another. We call this the roofing effect. This, what I'm showing you here, this triplet quartet combo, is a characteristic ethyl splitting pattern. If we've got some ethyl group, 2 hydrogens here next to 3, those 2 are going to split into a quartet, being next to 3. So there's our quartet. Then we've got 3 on our methyl that are next to 2. So being next to 2, those are going to split into a triplet. So the triplet and the quartet are being caused by one another. The quartet hydrogens are being caused by the triplet, and the triplet hydrogens are being caused by the quartet. So because these 2 peaks are related, they will kind of lean into one another. You'll notice that these ratios are not a perfect 1 to 2 to 1 for the triplet. The first and the third peak are a little bit lopsided. Same thing for the quartet. These are not 1 to 3 to 3 to 1 ratios. It's a little bit lopsided. That's called the roofing effect, and they will lean into each other if they are related. That's very useful because if you have another peak, let's say off to the side, you can tell that the quartet is not related to this other peak on the left. The quartet is related to the triplet because of the way it's leaning. So be aware of that. You can kind of use the roofing effect sometimes to tell which groups are related to one another. So let's look at a complex splitting pattern here that involves these multiplets. And let's figure out if we can explain what we're seeing here. Let's look at carbon A. Carbon with hydrogens A. That's a methyl ketone. So that should be at around 2.1. That looks like it's right here. 2.1 is right there. Notice that the peak at 2.1, A, is a singlet because the A hydrogens are next to none. Their neighboring carbon has no hydrogens. So there's nothing to split with. So they will be a singlet. Let's look at the B's. Notice that the B hydrogens, these two methyl groups, they're identical. They are on the same carbon, so they are in the same chemical environment. We've got 6 hydrogens there, but how many are they next to? These 3 are next to that one, the one on carbon C, and these 3 are next to 1. Again, these are identical. So we've got some hydrogens, type B, that are next to 1, and those are sp3 to sp3. They're all the same, so they should split into a doublet. Notice that B's should be the most downfield. They are the farthest from the carbonyl, the electronegative group. So the most downfield should be B. We've got 6 of them. The integration is shown here. We've got 6 of them, and B is a doublet. They zoomed in for us. B is a doublet here, and it's a 7 Hertz coupling constant. It's showing us that these guys are separated by 7 Hertz, which means that these are sp3 to sp3 neighbors. Then let's look at C. How many neighbors does C have? Well, C has 3 from those, and it's got 3 from those. So if he's got 6 neighbors that he's feeling, it doesn't matter that they're the same. The fact that he's got 6 neighbors means that he feels 6 different combinations of spin up or spin down. So these are going to follow the n+1 rule. If it's next to 6, it's going to split into a septet. So we've got 1, 2, 3, 4, 5, 6, 7. That's a septet, all 7 Hertz splitting constant, which means they're sp3 to sp3. Notice that the methyl ketone A and the methyl ketone C are fairly similar, but C has more carbons around it. So C should be a little bit more downfield than A because it's a tertiary carbon instead of a primary carbon. So a little bit more downfield for C. Our multiplet, our septet, is at 2.5. A comes next. It's our singlet next to none. So that's there at 2.1. And then lastly, our B's are the most upfield next to 1, means splitting into a doublet. And we've got the integrations 6 for the B's, 3 for the A's, and 1 for the C's. So tons of information here. We've got 3 types from 3 signals. We've got the splitting, which tells us what they're next to. We've got the shift, which tells us what their environment is. And we've got the integration, which tells us how many there are. Let's predict the spectrum here. First, I like to think about how many types of H's do we have. That means that's going to tell us how many peaks or peak clusters we're going to see on our spectrum. Now, they've labeled it for us, so it should be pretty easy, but you should be able to figure this out regardless. We've got 4 different types of hydrogens. Notice that we've got CH3s over here for D, and we've got CH3s over here for A. But these A CH3s are clearly different from our D CH3s. The D CH3s are on a carbon, that's on a carbon, that's on a carbonyl. These A CH3s are on a carbon, that's on a carbon, that's on an oxygen. So they're different environments. Also, clearly our CH2 is going to be a different environment than our CH, because the CH2 is next to a carbonyl and the CH is next to an oxygen. So we've got 4 different environments. A's are the same, the B, and the C, and the D. So you should see 4 peak clusters from this. The integration, we should have 1 for our B, 2 from our C, 3 from our D, and 6 from our A. That's what our integration should be. What should our shifts be? Let's think about what our shifts should be. Our D's are pretty standard methyls. They're 1 removed from a methyl ketone, so maybe our D's are going to be a little bit downfield from 0.9, but somewhere around 1 for our D's. Our C's are methyl ketones, so we would expect those to be at about 2 to 2.1. Now, there's another oxygen over here, so maybe that pulls it a little bit downfield. So maybe that's going to be a little bit above 2.1. Here we've got hydrogen on a carbon that's directly attached to an oxygen. So maybe these guys are going to be around 3, 3.5. And then we've got methyls that are on a carbon that are next to an O. So again, these are methyls, so they're going to start at about 0.9, but they're going to get pulled downfield by the oxygen. Now, we said that these are going to get pulled down from 0.9 as well. But notice that the A's are closer to an O. The A's are on a carbon, on a carbon, on an O. The D's are on a carbon, on a carbon, on a C, on an O. So the most downfield should be our B. B should be the most downfield. Then our C's, then our A's, and then our D. So we at least have a relative shift, and we've got a couple anchors. We know that C should be pretty close to 2, 2.1, 2.5. Let's figure out what our splitting should be. Remember, splitting, we go by how many neighbors we have. And again, since these are all sp3 neighbors, CH3 to CH2, those are sp3, CH3 to CH, that's all sp3. All these are sp3 neighbors, so they should all be 7 hertz, and so all of our n+1 rules should apply. So our D's are next to 2. Being next to 2, they should split into a triplet. So the D's should appear as a triplet. Our C's are next to 3. It should split into a quartet. So we should have a triplet from our D's and a quartet from our C's. Remember I talked about an ethyl splitting pattern, this triplet quartet, where the triplet and the quartet lean into one another? That's exactly what we have here. This is an ethyl group. So we should see that ethyl splitting pattern. How about our B hydrogens? We are adjacent to 6 neighbors, 3 here and 3 here. So if we're next to 6, that should split into a septet. And then our A's are all next to 1. So our A's should show up as a doublet. Let's look at our spectrum and see if we see that. We said that our D's were going to be the most upfield. Those are farthest from any D shielding group. And our D's should be a triplet since they are next to 2. So here's our triplet. And remember, we said it's going to be around 0.9 to start, and it might get pulled a little bit downfield because of the proximity to the carbonyl. This looks like it's at about 1. So that's fine. Here's our triplet D, upfield next to 2. Then we said after D, we're going to see the A's. The A's are also methyls, but they're a little bit closer to an oxygen. So our A's should show up next, and they are next to 1, so they should be a doublet. So there's our A doublet showing up after our D.
Then we would see our C's. We'd say C's should be around 2.1, maybe a little bit downfield because it's closer to an oxygen as well. Our C's should be a quartet since they are next to 3 over here. None on the other side, but 3 over here. So it should be our quartet. So there's our C quartet, a little bit higher than 2.1. And then lastly, the most downfield should be our B, since that's directly next to an oxygen. And that B should split into a septet. So here's our septet. The integration for 6 would be A. Our highest integration is A. That's by far our biggest peak. Our B should be our smallest peak over here. Our C should be next over here. And then our D should be in the middle, our second highest over here. So we've got number of signals. We've got integration of each signal. We've got the chemical shift of each signal. And we've got the splitting of each signal. Everything that we would have predicted in our spectrum shows up here. These are the general regions for our chemical shifts. For some reason, the book didn't insert a region for our methyls or for our alkyl, our normal alkyl chains. For example, primary, secondary, and tertiary hydrogens. Those showed up from 0.9 to about 1.4, 1.5. So that's this region here, our normal alkane, primary, secondary, tertiary hydrogens. From 2 to 2.5, we'll typically see hydrogens on carbons adjacent to carbonyls. From 3 to 4, we'll see hydrogens on carbon next to oxygens and halogens. From 5 to 6, we'll see our vinyl hydrogens, so our hydrogens that are on a vinyl group, so a carbon-carbon double bond. From 7 to 8, we'll see our aromatic regions. So from 5 to 8, these are all caused by diamagnetic anisotropy. From 9 to 10, we get aldehydes. And then from 10 to 12, or roughly 11 to 12, we get our carboxylic acids. Now, one last challenge. Let's deal with splitting when our J couplings aren't equal. When our coupling constants aren't equal. Let's see how this works. Let's look at this hydrogen first. He is next to one neighbor. Therefore, the red hydrogen will split into a doublet. But this is not a normal doublet because these relationships are not an sp3 hydrogen to an sp3 hydrogen. It's an sp2 hydrogen to an sp2 hydrogen. And in fact, those are trans. So we can look up on one of our slides the splitting constants for neighbors that are trans across a double bond. That relationship has a 12 to 18 coupling constant, which means this will be approximately a 15 hertz doublet. That's a doublet that is twice as wide as the other doublets that we've seen. Our normal doublets are about 7 hertz. This is going to be 15. So these are going to be two peaks at equal heights that are separated by 15 hertz on our spectrum. How about let's look at this red hydrogen. This guy also has one neighbor, our pink hydrogen, but that's also not a normal doublet. That's not a sp3 doublet. So they're not going to be 7 hertz. We can look up on our slide and we can find that relationship, a aldehyde hydrogen next to an sp2 alkene hydrogen, those neighbors are 7.7 hertz. So that's going to be, let's say, around a 7.5 hertz doublet. So we've got two doublets. We've got a wide 15 hertz and we've got a slightly wide 7.5 hertz doublet. But what about the middle hydrogen? That hydrogen is a little weird. This is what the splitting looks like for our middle hydrogen. It shows up at around 6.8, which is kind of what we'd expect. Normally 5 to 6 is for an alkene hydrogen, plus it's also got the ring next to it and a carbonyl next to it. So it's pretty far downfield. It's going to be at about 6.8, but it's not what we would normally expect. First of all, that's not a triplet. That H is next to one neighbor there and one neighbor there. So even though he's got two neighbors, it's not a triplet. But it's also not a normal quartet, because a normal quartet would be 1 to 3 to 3 to 1 as far as the heights of our peaks go. It's a 1 to 1 to 1 to 1 quartet. The slant that you see is just roofing effect. It's leaning into another peak because it's being split by something that's more downfield. What's more downfield than the red hydrogen is the blue neighbor. This guy's benzylic, so he's closer to the benzene ring. He's already 5 to 6 for being on the alkene, but then he's going to be closer to the ring. So remember that the N+1 rule only applies when all the neighboring hydrogens have the same relationship to the hydrogen being split. The relationship from the red to the blue is different than the relationship from the red to the green. That's why this is not a triplet. If this neighbor on the left was the same relationship to the neighbor on the right, then they would all have the same coupling constant, and it would be a normal triplet having two normal neighbors. So let's figure out what happens here. We've already said that the doublet from the blue hydrogen to the red would be a trans doublet, so a 15 hertz doublet. Red H to blue, that's going to be a 15 hertz doublet. We've already also said that green to red is a 7.5 hertz doublet. So we've already seen those two. The blue is going to be a 15 hertz doublet. The green is going to be a 7.5 hertz doublet. But we have to figure out the red by doing one of these splitting trees. What's going to happen first is the red is first going to be split by the blue neighbor. So that's going to split our red signal into a 15 hertz doublet. But then that signal is also going to get split again by the green. Remember that when we had multiple neighbors, they added on to one another. The red is going to get split up and down field by the blue, and it's also going to get split up and down field by the green, and those are simply additive or subtractive, depending on whether the spins oppose or align with one another. So the red is going to split with a 15 hertz doublet first with its blue neighbor, and then those signals are also going to get split into 7.5 hertz doublets by the green. So this guy gets split into a new doublet at 7.5 hertz, and this guy is going to get split into another doublet by 7.5 hertz. So we can go downfield and downfield. So basically have the spins up, up, or up, down, except that one is always going to be a greater distance than the other. The blue is always going to get split a different distance than the green. So we have up, up, or up, down. Then we also have down, up, and down, down. But because these are not all equal distances, up, down is different than down, up. And that's what's unique. Remember when we did a normal triplet, up, down, and down, up gave us overlapping peaks. They were the same. But now, because we have different separation caused by the different relationships, up, down, and down, up are different. And so we end up with these four individual peaks that we see here. 1, 1, 1, and 1. One signal, up, up. One signal, up, down. Another signal, down, up. And yet a fourth signal, down, down. That gets us our four individual peaks that are all separated by 7.5 hertz. Just a reminder, if these all had the same coupling constants, if these were all, say, 7 hertz, then red to blue would be 7, and red to green would be 7. So we would first split our red to blue, 7 up or 7 down, and then we'd split with green again, 7 up or 7 down. And since everything's equal, these two guys align right here. They happen to line up right on top of each other, and that gets us our 1 to 2 to 1 triplet. So if all of our splitting constants are identical, then we end up with the n+1 rule pattern. If we have different coupling constants between our neighbors, we split the larger one first and then the smaller ones. And usually what that causes is our peaks to not line up. These guys do not overlap at the same chemical shift. So we get 4 different peaks instead of 3 with 2 overlapping. That's it for our NMR lecture or lectures. We're going to be doing practice problems on the board for workshop.